about one of those really interesting concepts, which is being developed by a great coalition of players. I think the things that are probably most interesting in our current moment about this technology are, first and foremost, this wave of announcements we've seen from the utility sector committing to net zero goals by 2050. And for those of you that haven't followed that, those goals almost always come with a great big asterisk, which says, we know how to get the first 60, 70, 80% of the way there. We can do more renewables and keep our existing nuclear plants online and do more efficiency and all that. But that last, somewhere between 40 and 20%, we don't have the technology to get there today while maintaining the resilience and affordability and reliability of our grid. So everybody's got this shared aspiration to get to 100% clean, but we don't yet have the technology to do it. And so that's the big puzzle. And a lot of different folks are trying to find the piece that's gonna fit into that puzzle and get us the rest of that way. And so I think what we're gonna hear about today is a really interesting concept in that space where advanced nuclear and energy storage have been reimagined, recombined, and are being proposed to be put together in an interesting new way to solve a lot of problems in a deeply decarbonized grid, all while maintaining affordability, which obviously has been something of a challenge in the nuclear space in the past decade, and this could potentially mean that has changed. And so I'm just going to now go ahead quickly and introduce our terrific panelists today. We've got Chris Levesque, who's the president and CEO of TerraPower. We've got Tara Nider, the SVP of Program Development at TerraPower. We have Dan Poneman, the CEO at Centrus. I'm sure everyone knows Dan, and of course, the eminent former at Department of Energy. And we have Chris Nolan, the VP of Regulatory Affairs, Policy, and Emergency Preparedness at Duke. And so these are three of the players of an even broader team that are all interested in trying to scale up something in advanced nuclear and are working together in a variety of ways on this, which I'll let them explain. So I'm going to first turn it over to Chris to take us from here.
Well, thanks a lot, Rich, and thanks to ClearPath for hosting this great event, and to Dan Poneman at Centrus and Chris Nolan at Duke for joining us in the webinar. So we've been working on sodium fast reactor technology at TerraPower since the company was created 14 years ago by Bill Gates, and most of that time we were working under the banner of the traveling wave reactor technology. We think that sodium fast reactors have great promise for for all of tomorrow's energy challenges, and that's why we've really been focused for 14 years. After when the company was founded, we looked at many different options and decided sodium was the way to go. I think a lot of you are aware of that, but about 2 years ago, we really focused in earnest on getting a demonstration program going in the U.S. And what that required us to do was figure out who our U.S. partners would be, and also to figure out how we could best suit this demo plant for U.S. utility needs. And so with the Natrium announcement that we made several weeks ago with Hitachi, that's really a result of that focus on U.S. demonstration and U.S. partnerships and U.S. needs. So beginning with Hitachi, we've just had a great start to our work with them, which began early last year. As TerraPower and Hitachi both have considerable experience in sodium fast reactors. TerraPower with our TWR work and lots of our folks who were on different government programs in the past, government sodium programs. And then I think everyone's aware that Hitachi has had great success with PRISM, including accomplishing some significant licensing work with PRISM. So as we came together with Hitachi early last year, we felt a lot of synergy, and we started to think about, hey, what does this plant need to look like? And Tara Nider, who's in charge of the Natrium program at TerraPower, she's going to fill in more detiles later. But what you're going to see is we kind of brought together the best of the best between the TWR and PRISM, and that's what Natrium embodies. The other thing we did was, if you think of a lot of the advanced reactor attributes that a lot of companies like us are shooting for, which is, the better cost, the better safety, waste reduction, non-proliferation benefits, we were able to accomplish all of those things together, again, taking the best of the best between TerraPower and Hitachi. But then we also did some thinking and some listening to what the utilities were saying us about the 2030 needs. And that's where energy storage has come in. Wind and solar, we think it's good news that wind and solar are continuing to grow in their presence on the grid. They're clean. That's a good story. But we're really seeing a problem that the US has never seen before, which is managing the intermittency of wind and solar on the grid. We know there's different energy storage technologies out there, including batteries. But as we came together and shaped Natrium with Hitachi, what we saw was that thermal energy storage is really a great companion to sodium fast reactors. In the concentrated solar industry, there's been a lot of work on, because they've had to manage their intermittency, there's been a lot of work on molten salt storage. And it turns out if you take some of those systems and combine them with a sodium fast reactor, you have a really great solution. And again, Tara is going to get into more of these details. It's also a really elegant solution in that we've taken, a sodium fast reactor technology, we've modernized it with, things like the advanced physics that TerraPower has been working on for a long time, advanced materials, advanced component work that Hitachi did, for example, with their, their electromagnetic pump. And we've supplemented that with this new thing and solved a new problem for the 2030s, which is, the need for storage. So we're really excited about that. I do want to come back to economics. Tara's going to tell you more about how the novel architecture of Natrium really enables a lower cost plant. We also did some listening to utilities. We know that the idea of a capital project over $1 billion is really untenable for U.S. utilities. So we've targeted a plant that can, a commercial plant that can be sold for $1 billion or less in capital. Our utility partners have just been super in this effort. They're helping us understand the licensing needs, operations and maintenance needs of these plants. And they're also giving us really good insight on, what do they need in the 2030s as solar and wind grow. And so I do want to mention all our utility partners. They're Energy Northwest and Pacificorp. And then, of course, Duke and Chris Nolan from Duke is joining us today. One other thing that, while I'm talking about these partnerships that has come into play is Dan Poneman, our friend at CEO of Centrus, and I have been talking about the kind of chicken and the egg situation with HALEU for some time, high assay, low enriched uranium that our reactors need. And as a result of the discussions and as a result of, for our demonstration project, the Natrium demonstration project needs HALEU in the pretty near term, we decided that we would just start working on investing in HALEU capability. And Dan's going to tell you more about what's been going on in HALEU, but so glad he joined us today. And the last thing I'll mention, talk mainly about the technology, but in addition to, with Hitachi presenting a winning technology, we also think we've brought together the kind of business plan that we need to succeed in U.S. demonstration. So, kind of begins with having great delivery partners. And I should also mention Bechtel is on our team. So it begins with great delivery partners. Also includes significant private investment. As we work with utilities in the U.S., we really realize that, hey, it's not their job to take technology risk. Okay, their job is to provide power to their ratepayers at the best price. It's never been their job to take technology risk. those risks really need to be on the back of the private investors and the U.S. government. You know, there's several U.S. government programs out there now that are helping us get into demonstration. So one of the key strengths of our business plan, on top of the great technology, is the fact that we can engage utilities like Duke, get their best insights on their needs, get their best insights on licensing and operations and maintenance, but we're not putting them in the in the first of a kind risk situation. The plan with our business plan is that as we move through the demonstration project and achieve different milestones and confirm the grid connection date, that's when we'll begin to work with our utility partners to monetize the future power of the plant. And again, that's a really novel thing in our business plan. We're very excited about all of this, looking forward to the discussion today. And I think you'll find Tara's discussion on the technology to be, really, really interesting.
Chris, thanks so much. To our audience, as folks start to have questions, if you could please start inputting those into the Q&A function. We'll be monitoring that, and I'll tee up those questions for our discussants here as we go. Chris, I'm just going to ask you quickly, and I'll sort of leave it to Tara to talk a little bit more about the economics, which I think are a really interesting part of all this. As I just think about the structure that you've created here, I know that you were already, TerraPower and GE were already working together on the versatile test reactor, so the user facility at the Idaho National Laboratory. That was kind of a start of a collaboration. I've often thought, there are so many players now in the advanced reactor space, and frankly, not that many opportunities to commercialize things, whether they're, the couple of companies that are chosen for programs at the Department of Energy or by utilities. So, I think it's terrific the way that you've come together with GE on this to try to, take the best of all your expertise. I wonder if you can just tell us a little bit more about how that happened and that you decided to sort of join forces in this.
Sure. This has been going on since early 2019. These discussions with Hitachi, and they picked up momentum as we went along. Again, culminating in the announcement of Natrium. As far as what it takes to form that kind of partnership, I think it doesn't work with just any two companies. You can't just decide you're going to partner with a company and make it work. There needs to be natural synergies. And we found that we had those with Hitachi. So it began with both companies having considerable experience working with sodium fast reactors. There were also really complementary things about our two companies. One being we're a small technology company. They're a large, NSSS company. And as we worked more and more with them, we kept finding not just synergies, but complementary situations, where, okay, we had done some work on advanced fuel and materials. They had done some great work, as I mentioned, on, their EM pump. They had done some great work in licensing. And this, these lists of strengths on both sides of the page kept lining up. The other dynamic that started to happen was, we had great business discussions, but also our technical people just really hit it off. And I think, good engineers get along well with good engineers when they respect the folks at the other company. And they think that, hey, these folks, at Hitachi or TerraPower, depending on where you're sitting, they can really help us. We like working with these folks. They're helping us get to new levels. That's kind of how the partnership, moved along. And then, bringing on other folks like Bechtel, who happen to be working with us on the VTR, bringing utility insights in as well. It's really been this progressive thing. But I, would say that, you have to start with by picking the right folks and having the right natural synergies. And then if you're, if you have great open communications, I think you can really build up some speed. And that's what we've done.
Great. So we're going to turn to the second Chris now. Chris Nolan, I wonder if you can tell us a little bit about Duke's role in this.
Sure. Well, Rich, I think you led off the meeting very well, talking about the challenges facing utilities to achieve net zero, and And I think Chris talked about the intermittency of renewables and the importance of storage. And that's really one of the things that we're looking at. And so our carbon reduction goals at Duke are to reduce by 50% by 2030. And we're largely going to achieve those goals and achieve those goals early. We've expanded our renewable portfolio. We're the #2 solar producing state in the country. We've also transitioned from coal to natural gas through early retirements, which has really maximized value to our customer in terms of reducing our carbon footprint, as well as providing low-cost power to our ratepayers. And we're operating our nuclear fleet at a high capacity factor. We have 6 sites in the Carolinas with 11 units. We produce more than 50% of the power in the Carolinas from nuclear power, and about 84% of the enterprise's carbon-free generation is from nuclear. So nuclear will play an important role going forward into our future. Our goal for net zero is 2050. That's a more challenging goal to meet. To achieve that, we need to transition away from natural gas. And we've also determined that we need a fuel, right? The intermittency of renewables, whether it's wind or solar, really can't be compensated fully by storage. So we're looking at nuclear as a piece of our future. So we've are renewing the licenses for our existing fleet out for another 20 years to operate through 2050. But we're also looking at what we'll need to replace that as we start retiring natural gas plants. And so we continue to maximize the operation of the fleet, and but our need out in the mid-2030s and beyond is to have a base load generator that's zero carbon emitting. Really, we need it to be load following because that maximizes our ability to bring in solar and wind. But we also need it to be carbon free to reach our net zero goals. And so storage becomes the key to the solution. And so we're looking at battery technology, but we're also looking at the Natrium reactor because the liquid sodium provides high temperature and low pressure, which makes the reactor safer and more efficient, which is important to our customers. But the molten salt loop allows us to integrate thermal storage, which allows us to delink the turbine from the reactor. So the turbine can follow the load on the grid, allowing us to maximize our import of solar while the reactor operates at steady state, maintaining its maximum efficiency. And so we are interested in this project because we are looking for solutions to come in to the future that help us achieve our 2050 goal. And we're excited about some of the things they're doing at Natrium.
Chris, I know another piece of your role in this is to help provide advice and guidance on the licensing process and that kind of that's consultation process. How has that conversation gone in terms of interacting early with TerraPower in all of this?
Sure. Well, we're on their advisory committee, and we both have experience operating nuclear plants for over 40 years and also applying for licenses for new reactors. So we are experienced in the siting process, the training of operators, the interface with the Nuclear Regulatory Commission. And so I think we provide value to the team that wouldn't normally be found with a GE or a TerraPower that's really focusing on the design of the plant. So I would say that we're an accent or a complementary skill set, but one that will help take the OE of the last 40 years of the nuclear experience and build it into the reactor design so it performs as expected the first time.
Yep. Now, Chris, I know your CEO Lynn Good is sort of famous in the nuclear industry for having said, betting on a new nuclear reactor can mean a bet the company move, right? It's just such a large portion of the balance sheet. This advanced reactor concept takes a different tack, right? Which is that it both attempted to sort of redesign itself for cost in
Right.
both relative terms and absolute terms. And so that means a smaller unit, right?
Right.
We wouldn't call it an SMR per se, but it's, kind of at that 300 megawatt range. And Tara will tell us more about the, specific design specifications there. But, I wonder how that is kind of being viewed, both by yourself and by kind of the other utility partners. And, is that the direction and the scale that you see the advanced nuclear conversation going forward?
So the introduction of renewables in sizable amounts has given the transmission system and distribution system a little bit more of a distributed feel, right? Because we're bringing power into the system from many different places. And so the idea of bringing in power into the transmission system in smaller increments is attractive to us because it pairs with renewables better. The liquid sodium has a higher specific heat capacity. The components are smaller because it operates at atmospheric pressure. The support systems are reduced. And so the reactor design is a much more simpler and eloquent design, which will also reduce its cost as well. So we think that from a reactor standpoint, the size and concept is right. And then the storage concept adds value beyond the reactor design.
I'm now going to move on to Dan and to tell us a little bit about Centrus's role in this concept and the prospects of a HALEU supply linked into this, which for the lay audience members is high assay, low enriched uranium, which is the higher test fuel that a reactor like this needs to run.
Yeah, try to say high assay, low enriched uranium 3 times, and then you'll see, Rich, why we say HALEU. HALEU pass. So look, the Nuclear Industry Council did a survey earlier this year to advanced reactor developers and said, what keeps you up at night? And the number one answer was the access to HALEU. And so there has been, as Chris Levesque, my good friend, had mentioned, this chicken and egg problem. And by the way, before getting any further, I got to thank you, Rich and ClearPath, for being such thought leaders in this, and say how delighted we are to be partnering with terrific friends and colleagues at TerraPower. I've known Chris a long time, and Tara and Duke is legendary. And I think Chris just gave the most eloquent description of the intersection between nuclear and the intermittent source of supply that will allow us to get to the net zero that all of us really want to get to. So how do you solve a chicken and egg problem? Well, you got to solve both of them together. And that's where the Advanced Reactor Development Program came in and presented us with this unique opportunity. And our ambition at Centrus, since we have this, as many people know, contract with the U.S. Department of Energy to build on an 80-20 cost share basis with $115 million contribution from DOE, 16 advanced centrifuges that will have by early 2022 an NRC license to produce 19.75% HALEU. And the question is, what next? And one swallow does not make a summer, and 16 machines does not make a capacity. But if we are to supply the industry, we need to build out from there. And that's where the partnership, and I couldn't agree more with Chris in terms of starting with a relationship we already have many years past, back to the days of the TWR, came to the fore. And we were just talking about how we, as Centrus, wanting to supply HALEU to the whole industry, could team with TerraPower, and realizing that the needs for HALEU would be substantial and that 16 machines wouldn't really get you there. It was sort of a natural logic that came to the fore that led us to decide that we want to team together. So if they're successful, we are going to be able to build out from that initial cascade to something much more significant. And that would be the rising tide that would lift all boats in this industry, because it's good for TerraPower as well if others need this HALEU, because it's highly sensitive to the production rates. And the more of the stuff we produce, the cheaper it is for every consumer of the HALEU. So it's worth mentioning, and I don't want to go on too long, Rich, that there's a very strong national security element to all of this. And for U.S. national security purposes, we will ultimately need an enrichment technology that is homegrown, that's U.S. origin, which is what we have, and that that need dovetails with the needs of the commercial industry. This is not a novel idea. Eisenhower and Rickover solved the problem before when they leveraged the investment that we had in the nuclear navy, where Chris Levesque spent his early career, into shipping port and the whole dawn of the U.S. commercial nuclear industry. Well, it works, and we've got an endorsement for that approach in the Nuclear Fuel Working Group report, which I think aptly noted the need that the United States has for a long-term solution to the front end of the fuel cycle, which is not just mining, but it's also conversion and certainly enrichment. And we've seen other ways that have been used in the past in terms of like the Strategic Petroleum Reserve, which could give rise to a HALEU reserve. And we've also seen in DOD a strong interest in microreactors, many of which will also require HALEU of U.S. origin. So in a nutshell, really, I view this TerraPower thing as, to borrow Chris's phrase and both Chris's phrases, an elegant solution to an industry-wide problem, to actually a global climate problem. And if we could just get past this chicken and egg proposition, I think the future for advanced nuclear is truly bright and very exciting. We couldn't be more thrilled to be joining such a varsity team as TerraPower has put together. And the last thing I'll say is something about scale, because back in the old days, we used to only think about very large 3 million SWU facilities that were $5 to $7 billion. Well, nowadays, we don't need to do that. We can build out modular cascades. And so we can keep pace with, but not exceed, the demand for the HALEU, which is very important because capital costs are everything. And this is how we can keep a lid on our costs. And in that way, since you can actually build enrichment capacity faster than reactors, we can keep everything in check and in sync. So we think that this is truly the beginning, Rich, of the front end of a very exciting phase, not just for TerraPower, but actually for making the kind of sharp bend in the curve of climate change that, tragic fires in the Pacific Northwest and the hurricanes belting the Southeast and the Gulf Coast tell us that is the urgent problem of our day.
Needs to happen. Yeah. Dan, when you think about this, and obviously the modularity is a piece of this, which makes it easier, but when you think about kind of going from, you've got your pilot program, your 16 machines, you're entering into NRC licensing, to, ideally at one point, needing to be at enormous scale, fueling, a whole fleet of, probably a couple of different advanced reactor designs out there at different scales, running this. What's the biggest hurdle to you in that scale up going forward?
I would say, Rich, to me, the answer is very clear. Timing. We're going to have early 22, we're going to be up and running. But, Chris talked about the need for utilities to avoid taking technology risk. In the long run, the desirable thing for us would be to see long-term power purchasing agreements that give rise to guaranteed cash flow, which enable project finance. So the time for that commercial demand to mature is probably a little longer than early 2022. And so the biggest challenge we face today is to bridge the gap. When I was running, helping to run the Department of Energy, we used to talk about two valleys of death and the deployment of, at that time, the first grid scale solar PV through the loan guarantee program. We need to bridge a similar valley of death between the demonstration of a 19.75% capability under NRC licensing with the financial requirements to build out that much larger capability. And frankly, it ain't rocket science. The obvious answer to that is that it is and must be a governmental priority. This, I would echo again Chris Levesque's earlier comments. This is a place where investors and the government have a significant role to play in helping us to bridge that gap.
Great. Thank you, Dan. Tara, we're now going to turn to you, Tara, who's leading this project at TerraPower, to walk us through the design. And I think she's going to share a presentation.
I am. If I can get it to work. Okay, I'm really pleased to be here because Natrium is a really exciting reactor. We started talking to GE in March of 2019, and it became really clear, as Chris mentioned earlier, that it was going to be beneficial for both parties. Now, can I get this to go down? There we go. So we officially announced our cooperation on August 27th of 2020, and the team brings together two very strong companies in the development of advanced reactors and combines the best attributes of both the GE Prism and the TerraPower TWR reactors. The real key to success, though, I think, is that we decided we weren't really going to focus on the Prism or the TWR, but we were going to take the best of both of them, and if they weren't the best, then we were going to find something else. So our real focus was all about improving the economics of nuclear, because if we don't have the economics, there's really no point in developing a reactor. And the outcome was Natrium, and it really exceeded both companies' expectations. This slide shows how the two partners formed complementary expertise. GE has been around, I think, since the beginning of nuclear and has a very strong nuclear culture and a diversity of experience and energy solutions. TerraPower is a much younger company, but we've been focusing on advanced reactor technology, and we perform a tremendous amount of testing on our design. So we learn a lot, and we learn it very quickly. We have access to partners and private capital and a strong innovation culture. The team really just fell into a really strong working relationship to produce solid results. The Natrium design is really as simple as possible. The nuclear island sits on a small footprint of about 16 acres. It's decoupled from the energy storage and balance of plant. We designed it to cost, which meant that we needed to focus on how to construct the plant quickly and efficiently and keep it as simple as possible. The plant can easily integrate with renewables. The nuclear plant will run at 100% power, 24 hours a day, 7 days a week. But when the power demand is low, the heat produced by the reactor is stored in the molten salt tanks. And when power demand is high, the turbines get ramped up to produce up to 150% of the nominal reactor power. The plant has a very high thermal efficiency of about 41%, dependent on the operating conditions. As you see here, the nominal nuclear plant power is 345 megawatt electric. And I saw in one of the questions is why that's small, and doesn't the economics go down when you reduce the size of the reactor? It's not as optimal for us. We would like to go bigger, but we are really trying to match what the needs of the market were. And also with a smaller reactor, your risk of performance goes way down as well. So both companies are really passionate about sodium as a coolant. It has properties that facilitate a fast spectrum. It's not a moderator like water. We operate at very low pressures and high temperatures. There's a significant delta between the melting point and the boiling point of sodium. So at room temperature, it's solid, so you can transport it. It melts at a really low temperature, so when you're not producing power, you can keep it still above the melting point. And then, of course, you've got a really big delta to boiling, so you don't have to worry about boiling and having the coolant boil away. The sodium metal is non-corrosive, which leads to long life components with less maintenance. The plants that have been running for decades showed no corrosion from the sodium. It's also highly compatible with the structural materials in the fuel. And finally, it has really high thermal conductivity, which results in easy decay heat removal. GEH and TerraPower have reinvented what nuclear can be. We largely started by blowing away what a reactor looks like and breaking it into its individual parts. Then we started putting it back together, and nothing was considered sacred. We even considered the merits of a loop reactor instead of a pool reactor. We looked at a thermal spectrum reactor rather than a fast reactor, but we ultimately settled on a sodium fast reactor of the pool type and we kept some of the key parts of both the TWR and Prism. Starting with the basic concept, we tried to reinvent things in different areas to focus on the economics. We have new fuel, we have significantly smaller safety case, we've simplified the buildings, we've provided space-efficient heat exchangers, we've improved the fuel handling, we've incorporated passive reactor vessel air cooling system, to name a few. But the most visible change that you can see is really the incorporation of the integrated energy storage system using nitrate salts. Instead of a sodium intermediate loop, we replaced it with molten salt. And the funny thing is, a sodium reactor is actually a really good temperature fit for the molten salts currently being used by concentrated solar power plants, maybe even more so than molten salt reactors, and that's because of the temperature that they run at. So some of the benefits of using molten salt is it reduces technology development. There are multiple, I think 180 concentrated solar power plants that have this type of storage today. We are taking advantage of an existing supply chain. The sodium water reactions are now eliminated, and finally it enables the energy storage. How does the energy storage benefit us? Chris Nolan has already talked to us a bit about that. We can load follow with a reactor capacity factor equivalent to a base load plant, and the nuclear plants have really low variable cost. Our fuel costs aren't that high, but the capital cost is big, so you don't want to shut down your big capital plant that and keep it from running. It's not cost effective. When the cost of power is low, or when we don't have much need, we store the energy in the salt, and then when it's needed, we can release that, and the turbines and the steam generators will create the power there. There we go. So the number of storage tanks and the turbine size are all based on the customer's need. We can have as many as you need or as large as you need. And the steam generator trains are based on the size of the turbine. We did do some studies and decided that about a 50% overage on the power was what we thought was ideal, and that results in about 5.5 hours of storage. This next slide depicts a simplification of how the energy storage works. You would store power when renewables are producing power and discharge when they're not. Natrium runs at an ideal temperature for the energy storage, as I mentioned before, because the temperatures are high enough. If you were looking at a light water reactor, they run at a much lower temperature. So in order to match with that salt that the sodium is using, you would actually have to put booster power in there and increase the temperature before you would get the benefits. But natrium is already there. And so the energy storage allows the reactor to run at a steady output, which minimizes unnecessary cycling of the reactor, and power can be sent to the grid above and below the nominal reactor power. We are modeling different electricity markets. This one's for a 14-day period in August in California. So you would ramp up in the morning, charging the tanks. Between 6 and 1 p.m., you would 6 a.m. and 1 p.m. you would hold even the load, and then in the afternoon you would ramp to peak load, discharging the tanks, and then at night you'd start ramping down, discharging the tanks, and then finally you'd start that cycle again, charging up the tanks again.
You know what, Tara, can I ask you to stop sharing and restart sharing your screen? I think it's frozen for some of us.
Oh, you're right. Sorry about that.
No problem. I wanted to see the graph of the power market.
Is that it? Can you see it now?
We've got it. Thank you. Yep, we've got it.
Okay, sorry, I must have pushed the wrong button or something.
All good. We saw that go forward. Thanks.
Okay. Okay, so Natrium has many special features, and I'll run through a few of them. The building spacing is developed for parallel construction, nuclear and non-nuclear, and allows for construction access. The building construction can be modular when it's most economical, but not necessarily modular. We don't do modularity just for modularization. It has to be economical. And the site spacing allows distance for security. This is a cross section of the reactor building. As you can see, the reactor itself is underground, and it's a pretty simple structure. We don't have many internal walls because there's nothing really to protect there. Really, all of the power generation is in the reactor itself. So what's different? Natrium is leveraging inherent safety to drive out costs in construction and staff necessary to operate the plant. The Natrium safety case is compact and essentially constrained to the reactor module itself. Safety-related heat sink is in continuous operation because it's air that's flowing by the reactor. There's no control function required to activate the heat sink. Control rods are inserted by gravity, so you don't have safety-related operator function required. The coolant is liquid metal, so there's no high pressurization or phase change, which could challenge containment of the radionuclides. And all this drives an open floor plan reactor building, which is easier to construct because there are very few internal walls and very little equipment inside the reactor building other than the reactor itself. This slide shows a 2-unit site, and as you can see, there's a red line there that separates the nuclear island from the turbine island. So what this does, and we've been pushing this really hard, and there is some precedence with the PRISM on this, is that on that blue area there, the nuclear island, you're going to have the nuclear quality and NQA1, and nuclear construction methods, etc. But outside of that, you can use commercial construction methods. And what that does is the NRC and the designer and the owners, for that matter, can focus their attention on that blue region where you need to ensure that the plant is safe, that it's protecting the workers and those that live around the nuclear plant. And while those other things are less important, and the NRC does not have to have any involvement in that whatsoever. We call this decoupling. This is just a picture of the simplicity of our Natrium radiant vessel cooling. As you can see on the LWR side, there's a spider web of piping and a lot of Section 3 piping welds. Its safety case is not compact. It takes a lot of external piping, valves, heat exchangers to contain the pressurized water so it doesn't boil out of control. And then on the Natrium side, it's very compact, enabled by our coolant, which is extremely thermally conductive and remains liquid in essentially atmospheric pressure. This makes it possible to remove heat directly from the surface of the reactor naturally by circulating air. We have no safety-related piping welds above 2 inches, whereas an LWR has more than 2,600. This results directly into cost of construction reductions. This is because our safety case is so compact, there's very little that we need to put into the reactor building. The reactor building contains the reactor, and that's about it. As you can see, this is another comparison of the light water reactor building versus Natrium. And here's another view of that. The open floor plan of the Natrium reactor building has almost no internal walls, which saves on schedule and cost for construction. And finally, to summarize, we tried to make Natrium as simple as possible with inherent safety. That eliminates a tremendous amount of support equipment and nuclear piping. We have exceptional heat transfer, passive air cooling, and run at very low pressure. We're learning from adjacent industry innovations and really focusing on cost instead of nice to haves. I think in the past, the nuclear industry was so focused on the licensing process that, and we kind of forgot about the economics. We lost sight of that, and we were able to set our own costs because we were different from everybody else. But now we realize that that has hurt the nuclear industry. We now need to focus really on how can we make nuclear power cost effective, while still ensuring that it is safe and efficient. And we believe that Natrium has done this, and not through complicated safety equipment, but by making it simpler so that it operates very simply and it's naturally less expensive. So thank you.
Tara, thank you so much. Can I ask you to go back a couple of slides to the slide that I think may not have shared on the screen, but where you were showing how a typical system would kind of dispatch over the course of a day on the actual power production side?
This one? Great.
Yeah. So, I think this is such a game changer for the concept of nuclear operating in this flexible way. ClearPath was really, happy to be part of the rollout a couple weeks ago of the Clean Energy Ministerial's Nice Future Initiative, which is the clean, the advanced nuclear part of the Clean Energy Ministerial. We've had a campaign on flexible nuclear energy, which is kind of a paradigm shift in the space. And, this is a design that potentially really offers that. The first report by Lucid Catalyst coming out of that campaign sort of showed that a reactor that could operate flexibly and could achieve an overnight capex of something like $3 a watt or $3,000 a kilowatt, actually could operate competitively even in the pretty punishing environment of the the U.S. wholesale power markets, even with limited kind of policy intervention. It sort of seems like you've created a design which could potentially do that. It is pretty jarring to the perception of nuclear, though. It's just as a base load unit. How have you started to think about just that perception and changing the perception that by integrating storage in this way, you could play in a more flexible way in a power system?
Okay. So first of all, we knew about that $3,000 per megawatt electric, and we have gone beyond that, and our goal is 2,800. So we do believe we're in that category, and hopefully even get lower than that. But we tried not to just overdo it. We're really looking at how do we cut those costs by actual real impacts in the design. In terms of storage and how do we show that, I really think that first of all, this technology is available. It is available in the solar industry, but what's unique is matching that with nuclear, and we'd like to see that demonstrated. And I think a demonstration would go a long way. It would be lovely to be able to build a Natrium reactor right next to a solar plant and see how those work effectively together. And I think you'd be very pleased with the results.
Yeah. I think the other thing that you sort of draw attention to is the fact that while concentrating solar power has really struggled in the United States, around much of the rest of the world, it has really caught on. And so there's just been a huge amount of learning in deploying these kind of molten salt systems in that space, particularly across the Middle East and North Africa. Just thinking about licensing this thing, obviously NRC has been very focused on light water reactors. That has begun to change. So there's currently a non-light water design, Oklo's design currently in full licensing. There's also a smaller reactor design, the NuScale design, which has just come through licensing. And NRC has some historical experience with the Clinch River breeder reactor. How do you plan, and maybe there's also a question for Chris Nolan, how do you all plan to leverage the experience that NRC already has on sodium as you're going into this?
So we have, I'll let Chris talk too, but we have already engaged with the NRC, and we're working on our regulatory engagement plan. We're also going to help us out a little bit because GE submitted their PRISM license back quite a while back, but it kind of set the roadmap for what would be acceptable and what would not be acceptable. And so, in fact, when TerraPower, before we teamed with GE, we studied that pretty aggressively and said, okay, these are the missing links. What are we going to have to do to get it licensed easily? And we're following that path.
So there's two factors that are independent, but they're working together in a positive direction. One is, the NRC has been doing reviews of new licenses since about 2007. They're currently in the process of rulemaking for a new Part 53, which would focus on advanced reactors. And so rather than a licensee coming in having to apply the existing regulatory structure designed for light water to a non-light water plant, the NRC is already asking themselves, how do I create a performance-based risk-informed framework for alternate designs? And the other is the simplicity of the design gives the NRC a reduced scope in terms of their review. A pressurized water reactor operates at 2,000 pounds. The liquid sodium plant is at atmospheric. Those are big design differences that make the safety argument much more eloquent and simplified for the liquid sodium plant design. And so there are a number of factors that are pointing in the positive direction, but the licensing process, including the environmental review for any new plant, is a regulatory risk and one that that will factor into the planning and our strategic approach.
Great, thanks, Chris, and Tara for a fantastic presentation here. We're going to turn now to some of the questions that have rolled in from the audience. I think unsurprisingly, we have a question about cost, sort of at the top of this list. And obviously, the nuclear industry is has many examples of strong claims on cost, which were then challenging to pursue. I wonder if we could talk a little bit more about that. And this is probably for Chris Levesque and for Tara. Just for example, because you're going to operate in this flexible way, you've got a larger turbine than would be justified if you were just running that, all the time directly off the nuclear island. And so, 345 megawatt electric reactor, 500 megawatt turbine, doesn't that inflate the cost, or how do you think about a trade-off like that and still maintain cost?
Sure, I'll start, and I'm sure Tara can supplement. We're a technology company. So when we think about our new designs, we think about what are the technology enablers to lower costs? What are the technology enablers to more safety, et cetera? Because we're in technology space. That's where we're starting. So, some light water reactor designs, as they improve from Gen 2 to Gen 3, the technology didn't really change fundamentally, right? They implemented passive safety features, risk-informed licensing, those kinds of things. But when we moved to Gen 4, we really changed the physics. We changed the basic topography of the plant. So we have a whole new horizon to work with for improving on cost, improving on safety. So what is that new horizon? Chris Nolan did a great job with this already. Lower pressure, for one. So lower pressure means lighter components, lighter piping. If we think back 10 years to all the attention on super heavy forgings that we were trying to get into Gen 3, remember, there was this big bottleneck in Japan Steelworks because we needed these 500-ton reactor vessels. Now we're talking about a reactor vessel and other components that have to hold atmospheric pressure. So maybe they can be welded in a shipyard or welded at site. We're not going to have to get the NRC and the whole utility team to go to Japan to watch the ingot get poured for the super heavy forging. So low pressure is a big game changer. And guess what? If you have lighter components, lighter piping, less of it, as Tara was showing with the simpler architecture, guess what? You need lighter civil structures, okay? And again, if we think about a lot of the sources of really high cost on pressurized water reactors, they were related to these very high pressure plants and considerations like pipe rupture hazards analysis. I mean, go look at a PWR containment today. You literally have to build your reactor vessel, your steam generator, and your pressurizers in concrete bunkers because you assume there's going to be some kind of event. So low pressure, huge game changer. Our sodium fast reactors operates hundreds of degrees centigrade below boiling. That, that lets you rely on, Tara was showing the air cooling for decay removal. That lets you rely on things like air cooling, which are very close to the reactor. You don't need some extra source of, safety related piping, bringing water into the plant. So there's these technology enablers to lower cost. That's where we start. And the work with GE in the last year and a half started with that, but then started to look at deployment things that could help reduce the cost. And you saw things like the smaller excavation, locating the power producing equipment outside the nuclear island. So I think to finish the answer to Rich's question, he was asking about, well, you will need a turbine generator rated up to 500 megawatts now, right? Well, as Tara showed, that's outside the nuclear island. So yes, it is a larger turbine, but it's not a nuclear turbine, okay? I think you have to imagine a control room for a plant like this. If you go in a control room today of, a Gen 2 plant in the US, you're going to see all kinds of secondary plant indicators and alarms in that control room. So because the fact is, transients in the steam plant affect the reactor operator, and they have to be addressed by the nuclear team and licensing and the nuclear design. With the architecture Tara showed you, we moved the power producing stuff outside the nuclear controlled area. And one of the reasons we can do that is because we have a large pool of sodium, which has an incredible heat capacity. And again, as Tara showed, that RVAX, that air-cooled decay removal that would operate with natural circulation. So these technology enablers to lower cost are just a great reason that the U.S. needs to move to Generation 4, because you open up totally new horizons for economics and safety when you move to new technology.
Chris, that was great. I think we've got time for one more question. We've had a couple of questions come in about fuel. So this is probably one for both Tara and for Dan. Can you tell us a little bit more about what kind of fuel, and can you tell us, how much business you're going to be giving Dan? How often are you going to refuel the thing? And is it similar to light water, or is it new on that front?
Tara.
Okay, we are using metal uranium fuel. And that really helps us on thermal heat transfer. Once again, we won't have to give Dan too much work, because ultimately you can keep this fuel in the reactor for a very long time. However, we would be refueling on the 18 to 24 month cycle like we do on light water reactors.
Was that, Dan, you're still on mute, but was that a requirement that you put in that you still had to? I think you're still on mute, Dan.
Sorry about that. All I got to say is the customer's always right. No. I mean, all I'll say really is to reiterate, I mean, there's a real elegance to all of this, including, the fact that the less frequent refueling is one of the major non-proliferation benefits. And I think, the suite of cost, safety, and non-proliferation benefits is a lot of the overall story that all of us are trying to promote. And I guess the only other thing to say is we will have plenty of demand if we can break the conundrum of the chicken and egg. And just as the first of a kind reactor is going to be more expensive than the nth reactor, that's also true for our build out. So we're very optimistic that this, real, to me, game changer, this catalyzing action between TerraPower and ourselves will really enable the fueling. It's been fascinating to watch the discussion over recent years and all the bow wave of enthusiasm for the reactors. But candidly speaking, apart from people like you at ClearPath, not so much attention has been paid on getting the fuel that you need in a timely basis. And I think that's part of what's exciting about the new cooperation that we announced last week.
Well, and many thanks for your leadership, Dan, on beating the drum for that and sort of making everybody aware that this was going to be a really large issue that we needed to resolve as a country, and not just for the civil side, but for the defense side as well. Unfortunately, that does bring us to the top of the hour. We had far more questions than we've had time to address here, but we have logged everyone's questions, and so we'll have kind of good guidance for the team here as they develop more materials and put out more about this really interesting concept. We've got contact information up here if you want to reach out with further questions, both for the TerraPower team and Jeff Navin at Boundary Stone. There, you've got his email and mine at clearpath.org. And with that, I thank everybody. We had almost 200 people calling in, which I think is a good sign that there's quite a lot of interest in this topic and in this concept. So want to thank everyone for joining, and I want to thank the terrific team of folks here from TerraPower and Duke and Centrus for sharing what y'all are cooking up here. It's a really, really exciting concept, and at ClearPath, we wish you the best of luck as you push it forward. Thanks very much.
Thank you.
Thanks, everyone.
Thank you all. Terrific. Thank you so much.
Okay, bye for now.